everyone for joining this seventh AI Chair OceaniX webinar series. So today, Frederick Lindsten from Linköping University will talk about deep Gaussian Markov random fields. So after his talk, we'll have some place for discussions and any questions you might have. So you can also send it in the chat during the talk, of course. So, okay, then, Frederick, if that's fine for you, I'll leave you the floor.
Okay, thank you very much, Maxime, for the introduction and for the invitation. It's a pleasure to be here to give this talk to this audience. So as Maxime mentioned, I'm working at Linköping University in Sweden. I'm an associate professor of machine learning. And I think this talk will be mainly focusing on the machine learning methodology and more than the applications. But I still hope that you will find it interesting and that you can see some possible applications of this in your field of work as well. So the title of the talk, as you can see, is Deep Gaussian Markov Random Fields, and it is based on a paper with the same name that was published at the International Conference on Machine Learning about a year ago now. And this paper I wrote together with Sidén, who actually did most of the work, so I was happy to be able to tag along on this paper. Sidén was then a PhD student, now a postdoc with us in my group at Linköping University. So as I mentioned, this is really a machine learning or paper focusing on machine learning methodology. And so will the talk, but still the type of applications that we're motivated by in this work are those found in spatial statistics. And I guess that is also the reason for why I was invited to give this talk for this particular audience. So the problem formulation that we're considering is that we have some data observed over a spatial region. And based on this data, we want to infer some latent spatial fields. So some latent variables or hidden variables that are associated to these spatial observations in some way. So as an example, we can consider this figure up here, which shows temperature recordings over a certain spatial area. And these are satellite measurements, but as we can see here, there are also some white regions here, and these are due to cloud coverage. So we have white pixels, we don't have any recordings of the temperature. And the task could then, for instance, be to, well, based on the observed temperature values, infer what the temperature is underneath these clouds. So the temperature would then be the latent spatial field that we want to infer based on these observed recordings. So in order to solve such a problem, we need some model for the latent field, which is able to capture and encode the spatial dependencies between neighboring values. So again, in this temperature example, we want to model the dependencies between the temperature values at neighboring sites so that we can actually infer the missing values based on the observed values. And this is a problem that is commonly studied in spatial statistics, and there are some common choices of models that actually, or that have this property of encoding spatial dependencies. And two such choices or two such models are the Gaussian Markov random field, GMRF for short, and the Gaussian process. I will return to these models a bit later, but before digging into the details there, we can make another observation here, namely that an alternative view on this data is that it can be viewed as an image. And indeed, this is the way that I have illustrated the data here in this figure. We plot this as an image where the different pixels in the image correspond to different spatial sites, and the value in each pixel corresponds to the measurement in at that site, so the temperature in this example. So based on this observation, we could say that inferring the temperature here behind the clouds, that can be viewed as an in-painting problem, which is a type of problem that is commonly studied in computer vision. And as you might know, when it comes to computer vision applications, the de facto standard models that are used today are convolutional neural networks. So based on this observation, maybe we can ask ourselves, could we just view these spatial problems as instances of computer vision problems and simply throw sort of a CNN model on this to solve it? There are similarities, of course, but as it turns out, it's not quite as simple because there are some key differences between these different problem domains. And specifically in computer vision, we often have an abundance of data. So we have a large collection of images, and we then want to train a model that can learn some complex structures or patterns from all of these images jointly. So we sometimes learn from many examples. Whereas in spatial statistics, there is, in comparison, a scarcity of data. And maybe we want to infer some spatial field from as little as a single image. So we have some recording, a single recording over a spatial region, and we want to infer this latent field based on this one image. This also means that we then need to encode the spatial priors explicitly in our model so that we can indeed propagate information from sort of the inferred values to the missing values. And it also means that it becomes important to reason about the uncertainty in the estimates that we make. So even though we can indeed estimate, say, the temperature behind these clouds based on the observed temperature values in neighboring or sort of in the other parts of the image, intuitively, we can't say for certain what the temperature will be behind the clouds where we don't have any measurements. And in practice, it can be important to be able to not only estimate the temperature, but also provide a range of plausible values of this temperature. So we need to capture the uncertainty in some way. And this is something that is more easily done with these more classical models from spatial statistics, which has this property built in, you could say. Nevertheless, motivated by the success of CNNs when it comes to computer vision applications and the similarity between these different problems domains, we still believe that there is something to be gained by using CNNs also in the context of spatial statistics, and that is sort of what motivated us to look into this, or to pursue this line of work. And in our paper, then we show that there is a formal connection between Gaussian Markov random fields and CNNs, and we, based on this connection, develop a new class of models that enable us to use CNNs also for solving our standard spatial problems. Okay, so let us then return to the background here and have a closer look at the GMRF model to make this a bit more concrete. And I can just maybe pause for a second and ask if there are any questions before I proceed. And also just repeat what Maxime said in the beginning, that you're of course free to ask questions during the talk if you want. Okay, no questions so far. So to develop this this new model, the deep GMRF, we'll start by reviewing a standard GMRF model. So a GMRF is essentially a model for some high-dimensional Gaussian vector x, which has a particular structure. So if x here follows a GMRF with a precision matrix Q, it's simply a Gaussian vector with some mean mu and precision Q. But related to or associated with this precision matrix, we also have a graph G, which is, you could say, an illustration of the structure of this vector. This graph consists of a vertex set V, or a node set, where the nodes of the graph correspond to the individual elements of the vector x here, so x, xi, xj, and so on. And we then also have an edge set E here, which encodes the conditional independencies between these variables, the elements of the vector x. So more specifically, if there is no edge between a pair of variables xi and xj, so if this edge here is not contained in the edge set, that tells us that the random variables xi and xj will be conditionally independent, conditionally on everything else in the graph. So put differently, if we look at the graph that I've shown you in this figure up here, which is a type of lattice graph that I will use throughout the talk. If I consider a certain variable here, or a certain node corresponding to a variable xi, what this graph tells me is that if I would know the values of the neighboring variables here, then the value of xi will be conditionally independent of everything else in the graph. So you can think about the edges here as encoding some kind of direct dependence between two variables. Equivalently, we can relate this graph structure to the precision matrix because it can be shown that if there is an edge between variables I and j, then this is equivalent to having a non-zero value of the corresponding ijth position of the precision matrix. So the graph gives us the sparsity pattern of the precision matrix. Okay, so the GMRF is then a model that we can use to encode spatial dependencies. And it can then be used as a prior for some latent field in application in spatial statistics. So what I mean by this is that we usually use the GMRF to encode the dependencies between the variables in this latent field x. But we don't observe x directly, but rather through some other variable y. And I will assume here that we have observations y at some subset of the spatial sites. So my observation likelihood is such that I observe a value yi for each value xi in some subset here of all the pixels or all the spatial sites, where yi conditionally on xi is normally distributed with mean xi and some variance sigma squared. And as I said, this product here can range over some subset of all the pixels in the latent field, which means that we can cover different cases here. So for instance, if the number of observed sites is strictly smaller than the total number of sites n, that would correspond to a type of n-painting problem where we want to infer missing values, like in the cloud coverage example. We can also cover the denoising setting here, where if this variance here, sigma squared, is strictly larger than 0, that would correspond to having some measurement error when we measure the value of xi in each site. So yi will not be precisely equal to xi, but we measure with some error, and then we can use this model to sort of filter out the noise in the measurements. So there's a question in the chat about sigma being identical for different I. We have assumed that in the model that we have used, and in all our numerical examples, we have made that assumption, but it's not strictly necessary. If you have some, if for some reason you want to use different sigma, you can do that. But of course, if you would use a unique sigma I for each site I, it can be problematic to learn these sigmas from data, because it's would be very easy to overfit. Right, so with this model in place, we both have the prior and we have a likelihood model here. We can then use that within Bayes' theorem to compute the posterior distribution over the latent field x conditionally on the observed data y. And conveniently, since everything here is assumed to be normally distributed, both the GMRF, that is a model for a Gaussian vector, and also our likelihood here is assumed to be a Gaussian distributed. It turns out that the posterior distribution will also be a Gaussian, and we can write this explicitly on closed form like this. And it follows that the posterior distribution over X conditionally on the data Y is also a GMRF, which will have the same graph as the prior, but with an updated mean and precision matrix. And for the precision matrix, we have this form here. We add essentially just an identity matrix here with IM here. M should be viewed as a mask, which corresponds to the indices that are contained in this subset M. So it's a masked identity matrix, and the expression for mu is given by this equation here. So that's nice. We have this closed form expression for the posterior that we can use to infer the latent field from the data. Still, if we want to use this model in practice, we need to, of course, be a bit more specific about how we construct the model, how we select the prior. And specifically, once we have settled on using a GMRF for this problem at hand, how do we actually construct the graph and the precision matrix of that GMRF, of the prior over this latent field X? And here there are some common choices that are often used in practice. So some standard off-the-shelf choices for how we can do this. And one such choice is the so-called second-order intrinsic GMRF. In this model, we assume that X is then following a GMRF with a zero mean and a precision matrix given by this product G transpose G. Where if we assume now that the graph has this lattice structure that I showed you before. So we have a graph which is such that we draw an edge between neighboring pixels, if you think about an image representation of this latent field. Then the matrix G here is such that it has the value 4 on the diagonal. It has the value -1 on the off-diagonal elements where there is an edge between nodes I and J, and it has the value 0 otherwise. So this is one sort of default choice that can be used, which has some nice properties. As a side note, another common choice here that I just want to briefly mention is to, instead of going directly for a GMRF model, we can model the spatial dependencies using a Gaussian process. And what I want to show here is just that there is actually a link between Gaussian process models and GMRFs as well. And specifically, if we assume that we have a Gaussian process with a Matern kernel, then this can be written as a solution to a stochastic partial differential equation of this form. And if we would then compute a finite difference approximation on, again, some integer lattice, so we compute a finite difference approximation to this SPDE, then this gives us a GMRF representation of the GP, or a GMRF approximation, you could say, of the GP. So for if you're more used to working with Gaussian process models, or if for some reason you want to start with a Gaussian process, maybe you find it more intuitive to model the spatial dependencies using a model of this type, then you can still translate that into a GMRF. And I just wanted to mention that to show that there is a relevance also for GP models here. Was that a question? Oh. Okay, but I will leave this GP connection for now and instead return to the other standard model, the second order intrinsic GMRF. And to sort of develop this deep GMRF model, we will start by rewriting this second order intrinsic GMRF in an equivalent form. So if you recall, we had this Gaussian distribution over X with a precision matrix G transpose G. We can equivalently write this by introducing a filter or a stencil, which I denote by WG. So this is just a small 3x3 matrix, which has this form here. So based on this filter, we can define X implicitly through these two equations. And what I mean by that, well, first of all, I introduce this upper case X here, which you can think of the image version of X. So if X is the Gaussian vector, then the uppercase X is the Gaussian, or it's a matrix which corresponds to this image view of this Gaussian vector. Or put differently, little x here is simply the vectorization of this matrix, uppercase X. Okay, so based on that notation, I then define another variable here, which is this Z variable. And I define that to be the convolution of this matrix X with the stencil WG. And if we then assume that the output or the result of this convolution operator is such that this matrix Z here is standard normal, so normal with mean 0 and identity covariance matrix, then it turns out that the distribution of X must be precisely the one that we had up here. So it must follow the second order intrinsic GMRF. And the reason for why I refer to this implicit definition is that we define the distribution of the output of this convolution operator to have a certain distributional form, and then that will implicitly say something about the distribution of X. However, based on this alternative formulation, you can now see that there is we're getting close to the connection to CNNs. Or put differently, we could view this second order intrinsic GMRF as a one-layer linear convolutional neural network. And this, of course, suggests a natural extension of this model to a multi-layer CNN architecture. And this is the deep Gaussian Markov random field model that we propose. And the structure of this model, well, it's shown in this figure here. So the way we construct our model is that we start with some observed data shown here, and this could again be some spatial observations where we might have some missing values. So these are indicated here by these black regions. They're missing values. We think about this data as being generated from some latent spatial field X. And the prior that we put on X is such that if we would take this image here and feed it through a certain number of convolutional layers, then at the end, after L such layers, we end up with a sort of a pure noise image. We end up with a hidden layer Z here, which follows a standard normal. More formally, we can write this using a set of equations. So again, saying the same thing that I mentioned on the previous slide. The way we define the deep GMRF is through these equations here. We assume that the first layer here is given by the latent field X. Going from the L-1th layer to the Lth layer is given by a standard convolutional operator. So we convolve our convolutional layer. We convolve this hidden layer here with some filter WL. We add sort of a bias term here, which is common in the deep learning literature. And then we apply some element-wise nonlinear activation function to this, which I did not see here. And then this will give me the next hidden layer. I proceed in this way for a total of capital L layers. And at the output of this CNN model, I assume that I have a standard normal distributed random variable. And again, this gives us an implicit definition of the distribution of X. And we can think about this as being defined through an inverse transformation. So if this set of equations here, that gives me a way of mapping X to Z, then well, I can equivalently view this as mapping Z to X through the inverse mapping G inverse here. And of course, then if I assign a certain distribution, like a standard normal distribution to Z, that will give me some distribution over X. Okay, are there any questions so far? Okay, for the rest of the talk, I will do something which might look a bit funny, at least if you are used to working with deep learning models, and remove this nonlinear activation function here and define a linear version of this model, a linear deep GMRF in the same way, but without the nonlinear activation. And if I do that, well, the entire mapping will actually be a linear mapping. So for this linear deep GMRF, each layer can be written as a linear, a bijective linear mapping of this form, where I have some matrix GL and some vector BL defining the mapping. And this means that the multi-layer model, if I simply concatenate capital L such layers, then the total of mapping defined by the model, that will be the composition of all of these functions, these linear mappings, and consequently the final distribution that I get for X is simply a GMRF with a Gaussian density given on this form, with this expression here, where the precision matrix is again G transpose G, and G here, that's simply the product of all of these matrices for the individual layers. And importantly, as a consequence of this, the determinant that appears here in the expression for the PDF, that can be written as the product of the determinant of the individual layers. Okay, well, if I do this, and as I mentioned, I end up with something which is actually just a standard GMRF, so a standard linear model, or standard Gaussian model. Then what's the point with this multi-layer architecture? Couldn't I just define this GMRF from scratch, sort of, to begin with? Well, as it turns out, there are a few beneficial side effects, you could say, of using this multi-layer architecture. And perhaps the most important is that by using this, this multi-layer structure, we can use small filters, small convolutional filters within each layer, which are constructed to have cheap determinant computations. And by, by this expression here, if I can compute the determinant for each layer independently, then I can also compute the determinant for the full linear mapping efficiently. And this is important because this determinant computation, that is usually the main computational bottleneck when working with these GMRF models. So by the multi-layer architecture, we can construct the filters to get cheap determinant computations. Still, we can obtain a model which has effectively a high order despite using these small filters, in the sense that it is capable of capturing long-range dependencies in the model. And comparing this to a model where we just specify a large filter to begin with much fewer parameters to learn. And furthermore, we get, this is perhaps a bit hand-wavy, but we have reasons to believe that through this multi-layer architecture, we also get some inductive biases that are beneficial when learning the model, similar to what has been found in computer vision applications on CNNs, that the different layers are sort of responsible for learning different features of the data. And finally, another benefit of this is that we can make use of standard computational tools from the deep learning community, like TensorFlow and PyTorch and so on, which have very efficient automatic differentiation tools. They have stochastic optimization algorithms and so on and so forth. And from a practical standpoint, I think this is perhaps the most important point, that despite having these rather complex models, using these existing tools, it's actually very easy to implement them in practice. Okay, so commenting a bit more on this first point here about the small filters with cheap determinant computations. So in our paper, we investigate two special forms of filters to enable this, which we refer to as the plus filter and the sequential filter, respectively. And these filters, they are both 3x3 matrices, which has, they have these particular forms here, where the A values here, they are free parameters that we can learn from data, but you can see that they are structured in a certain way. And both of these filters are such that we can perform density evaluations. We can evaluate P of X with a computational cost that is linear in the number of pixels in the image, you could say. So order n. And this is in stark contrast with a sort of naive application of a GMRF with which would have cubic complexity in n instead. Furthermore, we show that using this plus filter here, we can actually recover these standard models that are commonly used in spatial statistics, the second order intrinsic GMRF, as well as the GMRF approximation of the Matern GP. And this means that we can think about this linear GMRF as taking these standard models that are commonly used and used successfully in many applications, and then generalizing that into a richer class of models which has learnable parameters that we can learn from data. For the second order intrinsic GMRF, this result is quite obvious, and actually I showed you before that we could write this model using the plus filter, so with a single layer, where we would then assign specific values here, more specifically 4 in the center and -1 in these positions here. So in that case, we can get or recover the second order intrinsic GMRF using a single layer deep GMRF. For the Matern case, it's not so obvious, and there we actually need the multi-layer architecture, and we need to select the number of layers to be larger than this parameter gamma, which is the smoothness parameter of the Matern kernel. Right, so this model then gives us again a prior that we can use for our latent field. But in a practical application, we also need to combine this with data to infer some posterior over the latent field, right? So if you recall what I said before, we don't observe X directly. Instead, we have observations of some YI here related to XI. So we still face at least or two related problems here. One is that we need to infer the posterior distribution of X conditionally on Y. And the second is that in this model, we have introduced some model parameters, the filter weights in the CNN model. And we want to learn these parameters from data. And specifically, we want to do that by maximum likelihood. So we want to maximize the likelihood of the observed values Y with respect to the model parameters, which I denote by theta here. And unfortunately, it turns out that even though we have this property of cheap evaluation of P of X, both of these problems are still computationally cumbersome. And if we look at the expression for the posterior distribution, for instance, even though we have a closed form expression, evaluating this exactly will still be cubic in the number of pixels in the image. And similarly for computing the marginal likelihood of the data Py, which would need to learn the parameters. So we need to address these two problems still. And focusing on the first of these problems here, computing the posterior distribution, let us assume for now that we have found some model parameters. So we have estimated the filter weights and the bias terms in the CNN model. And the task is simply to infer the posterior distribution conditionally on the data. The way we propose to address this is to use a conjugate gradient method, which allows us to, first of all, compute the posterior mean of this distribution, and also to generate samples from the posterior, which we can use then to estimate the variance, for instance, if we're interested in using the variance as an uncertainty or a measure of the uncertainty. And compared to using sort of a naive computation of this posterior distribution, this reduces the computational cost from cubic to roughly in the order of n to 1/2. Importantly also is that this conjugate gradient method can be implemented using only matrix vector multiplications, and multiplications with matrices G and G transpose can be implemented using only convolution operators, so in a matrix-free form. And this is quite nice when it comes to implementing this in practice, because it means that we never need to form these matrices explicitly, which would be a bit cumbersome, at least, or require non-trivial sparse matrix representations. But instead, we can simply use built-in convolution operators in TensorFlow is what we have used in our implementations to implement these matrix vector multiplications. Okay, pause for a second and read a question in the chat. It was a bit long, so it will take me a minute. Okay, if I understand well, a main advantage of our deep linear structure is to efficiently deal with both small-scale correlations and large-scale correlations. Yes, you could say that. But I guess for your wavelet decompositions, modulated Gaussian noises will provide similar skills and be efficient for computing the posterior PDF. I think your example of Gaussian process with Matern covariance is actually a good example of multi-scale Gaussian random process that is well represented in Fourier basis, but I may miss something. I think this is correct. The problem, though, as we could see with the Matern covariance, is that if we, based on the value of the smoothness parameter, if we have long-range dependencies in the Matern covariance, we actually need many layers in this architecture. So in some sense, that would correspond to, I guess, a larger model in the GMRF representation. Another advantage of this approach is that it allows us to learn the parameters of this model quite freely. So it's still a rather flexible model, even though we capture these models as special cases. It's much more flexible because we can learn the parameters of these filters independently, or not independent, but sort of we have individual filter weights for the different layers. So in that sense, it becomes a more flexible model than the Matern model, for instance. Which I guess then leads me into the second problem here about actually learning the model parameters. So the second of these two related problems that I mentioned before. And as I said, we want to do this by solving a maximum likelihood problem where we find the filter weights or the model parameters of the CNN model by maximizing the marginal likelihood or the log marginal likelihood. So here I want to integrate out the latent field X, right? Which again, unfortunately, turns out to be a computationally costly operation. And even though we could in principle use the conjugate gradient approach here as well, it's still too expensive because here we would actually need to solve or apply the CG algorithm in each iteration of, say, a gradient-based optimization method for solving this optimization problem here. And that turns out to be too expensive. So the proposed solution that we have here is to instead use a variational EM approximation for solving this problem. So very brief overview of what this means is that we introduce a variational approximation, which I denote by Q here. So Q is a distribution over the latent field X, which is some simpler distribution that is parameterized by some parameter phi. And the role of this is to approximate the posterior, which is costly to compute. We can then optimize the evidence lower bound, as is usually done in variational inference. And we optimize this jointly for the model parameters theta and the variational parameters phi. And once we have found a solution to this optimization problem, we simply discard phi. We throw away our variational approximation, and we keep the theta values that we have found as an approximate solution to this maximum likelihood problem here. So you could say that the variational approximation Q here, it's only used as an auxiliary quantity to learn the model parameters. But once we have found theta, we resort to the conjugate gradient method for doing posterior inference. And this means that we can learn the parameters in linear computational time, which is nice. And the way I like to think about this is that, as we said before, and it's quite common to actually use these more or less handcrafted models like the second order intrinsic GMRF, where you have essentially hand-picked values for the filter weights. And even though you might think that this is kind of a quick and dirty approximation to the maximum likelihood problem here, it still allows us to learn something. It gives us an approximate solution to the maximum likelihood, which I think in many cases will at least be better than this, these hand-picked values that are often used. Okay, so final part of the talk, I'll just show you some numerical results here to illustrate the model. So the first example here, this is a toy model that we consider just to kind of test the flexibility or the performance of the model. So what we do here is that we actually generate data from a return GP. We then mask out some regions in the image, these black boxes here, and the task is to impute these missing values. So if we apply here as a return GP model, this would be the true model here, because this is how we generated the data. So this is kind of the gold standard in this particular example. We can see that we get sort of an interpolation here, a smoothing of the data within the missing regions. And similarly, if we apply different versions of the deep GMRF, we get similar results, at least visually, but we have evaluated this a bit more in depth as well. And we get similar results here for different versions of the number of layers and then the different types of filters. But okay, here, this is not too surprising perhaps, and doesn't provide anything else than what we could solve with the return model. It just solves this by smoothing out the observed data. However, if we now introduce some artifacts in this data, so what we do is that we chop up the true data into different stripes like this and reorder them. And then we still ask the model to, based on this data, assuming that this is the true observations, impute the missing values. If we just use the return model, we again see that it's just smoothing out the data within the missing regions. It's not capable of taking this highly non-trivial structure into consideration. And similarly, if we use a model with a single layer, which is a standard GMRF model, again, we just get this smoothing effect. But as we increase the number of layers in the deep GMRF model, we can see that it starts to pick up on the edges that we have in the data and actually manages to impute the missing values respecting the edges that we have here. Oops. And looking a bit deeper into what happens here, we can see that the different filters that we learn if we, for instance, have a 3-layer model, the different filters in these 3 layers will correspond to edge detectors, essentially. So the first layer is responsible for detecting edges in one direction, the second layer detecting edges in the other direction. And in this particular example, the third layer is essentially just an identity mapping. It performs a little bit of smoothing. But that's, of course, a very toyish example. To also show you some more real-world results here, we can look at this example with the cloud coverage and temperature measurements again. And in this example, we actually have data looking like this. So these are actual temperature recordings. And here they're taken on a sunny day with not much cloud coverage. But what we do in this example here is to use the cloud coverage from a different day to mask out the data, which means that we get sort of a realistic looking data, the masked data here, but we also have the ground truth, so we can evaluate how well the models do on this. And the results that we get from our model are shown at the bottom here. The main thing that I want to mention here is that we do get both an estimate of the mean temperature, but also an estimate of the uncertainty here in terms of the posterior standard deviation. And looking at how this performs compared to some alternative methods that have been used to solve this. So this data is actually taken from a type of competition. So there are a lot of methods to compare with that we can look at. We actually perform quite well. So a particular version here with the sequential filter and 5 layers is the one that performs the best in 3 out of 5 different evaluation metrics that were considered in this competition. Right, so to summarize, so the deep GMRF model that we have proposed provides a formal link between GMRFs and convolutional neural networks. We have mainly looked at the linear version of this, which is a bit funny in a sense, but this is really a special case of a GMRF, but it nevertheless comes with many advantages. And in particular, with these small special filters that we consider, the plus filter and the sequential filter, we get cheap determinant computations. Still using the multilayer architecture, we can get the high effective order of the model to capture long range and complex dependencies, while still enjoying the fact that we have fewer parameters to learn than a fully parameterized large filter. And this gives us some kind of inductive biases, as we have seen in experiments. And we can use standard tools from the deep learning toolbox, such as variational inference, stochastic gradient-based optimization, autodiff, and so on and so forth. And we can then learn these models with variational EM in linear computational time, which is nice. And yeah, we can use this conjugate gradient method for computing the predictive mean, and we get an uncertainty quantification through sampling from the model and computing the sample variance. And that is all for me. Thank you for listening. And I realized that it took a bit more than 45 minutes, so sorry for that.
Okay, thanks, Fredrik. Very nice talk. Thanks again. Does anyone have any questions? You already answered 2 questions from the chat, so maybe any other questions?
Maybe one, Fredrik, thanks a lot for this talk. That's very interesting. And very much related to some of our interest, which is more on space-time dynamics, but basically very close. And maybe a question, I'm not sure if you understood the way you optimize or what you mean by the posterior mean before moving to the estimation of a parameter, but more for the reconstruction of the latent state from the observation.
Yeah. So here you mean,
yeah.
So once we have learned the model parameters, we fix theta. So we fix the filter weights in the CNN, but we still face this problem of computing the posterior distribution of the latent field conditionally on the data. And we have actually a closed form expression for this. It's simply the posterior for the GMRF that I showed you before. But computing that exactly is costly. It's cubic in the number of pixels. So we compute sort of an approximate solution to this using conjugate gradient. And the way we do that, well, we know that this posterior is fully characterized. It's a Gaussian distribution, so it's fully characterized by the mean and the covariance. So we can use the conjugate gradient method to both compute the mean of this posterior So the like the
Okay,
mean
and then
estimate of the latent field.
it comes to the minimization of some term. I mean, you express the posterior mean as the minimum of some.
Yeah, you write it as a linear system of equations, essentially, that provides you the solution to this system of equations is given by the mean of this.
Okay.
And you can get that by just reformulating the expression that we had in for the posterior mean, if I can find it now.
Okay, got it.
Now I didn't
So you
find
go
it there,
back to.
it was probably here. Here. So this is the thing that we want to compute here, right? So you just write this as q tilde mu is equal to this expression.
Okay. And here I think that would be the same for parameters. If you move to the nonlinear version, you won't have any more those closed forms expressions, right? Or can you keep them?
Yeah. No, then we don't have these closed form expressions. So what we can do, and what we have tried, is to use the variational approximation both for learning the parameters and for doing posterior inference. And actually, we actually do that already, because going to the, I said about the learning here, the variational EM, we actually have this approximation to the posterior. So, and this we can do also for the nonlinear model. So we could just be happy after solving this variational EM problem, and then we have the model parameters, we have an approximation of the posterior, and we can use that for drawing inference about X. What we have found, though, is that so far we have only experimented with very simple variational approximations, and in particular, this sort of standard choice, the mean field approximation, which factorizes over the different components. And we get a fairly good estimate of the mean, but we get a quite severe underestimation of the variance, posterior variance in Q.
And,
so
and here you use, when you use standard version here, you use like that's implemented again as a neural network, I assume?
No, so Q is actually very simple. So what we say here is that Q is just, it's again a distribution over all the spatial sites, but we assume that this factorizes. So you assign as an independent factor for each site, which is a normal with a mean, certain mean and a certain variance, and then we optimize the mean and the variance independently for each site.
Okay. And here, just to understand again, while your case studies, you assume you have only one sample, one image to both for a parameter estimation and reconstruction.
That's what we have considered, yes. And that's sort of how it was formulated also in this comparison that the competition that I mentioned. But you can of course think about having more data, more images for learning the model, for instance, and then once you have learned the parameters, you apply that model to a specific image.
Yeah. Okay. Okay, thanks a lot. I may have one additional question, but I may let the floor to others for questions. Thanks a lot.
I can just mention that this improving on the variational approximation and generalizing to the nonlinear case, that's something that we're currently looking into. And even though we have a solution that's up and running, for the results that we had, at least when at the time of publishing the paper, the linear model performed better. So that's why I focused on that here, but we hope to improve the nonlinear version as well.
We've applied quite similar ideas on space-time dynamics.
Okay.
Using those very elbow frameworks and using CNN-based parameterization or recurrent networks parameterization for Q. For which we got some result, and maybe John could comment on this if you're interested in this. I think that's correct for the mean, the same as what you mentioned, and in some cases it might not be very, very good for the variance component. It's what I remind also.
Interesting, and that's also something that we have discussed as a generalization here to go into the space-time domain as well.
Okay, thanks again. Thanks. I think we have two other questions from Redwan in the chat. Maybe Redwan, you can ask your questions.
Yeah,
sure. Hi, everyone. And thanks, Frederick, for the nice presentation. Yeah, I had two questions. The first one is about how you deal with padding, especially when you use a deep linear convolution. Do you use like padding same, or do you just keep the boundaries, or you just leave them, disappear? Or how do you deal with padding here?
Yeah, we use same padding.
Okay, so
TensorFlow notation. So yeah.
All right, but is it a zero padding, or you just replicate the boundaries?
I believe that we use zero padding now.
Okay. All right. Second question is between actually these two type of filters you shown, the one that is named plus and the other one which is named sec filter. Do you find any big differences between using both, and do you have maybe any idea when to use one and the other?
It's a good question. I think in our numerical evaluation, the sequential filter actually turns out to be slightly better in most cases. I don't have a good explanation for that. And I was sort of a bit disappointed because I think the plus filter is more elegant. So I was hoping more for being able to recommend that. But let me see if I have some results. Yeah, here you can see that. I mean, this is just one example, of course, but here the sequential filters with 3 and 5 layers performed better than the plus filters.
Okay,
I think that was quite consistent, but I don't have a really good explanation for why that is the case.
All right. Thank you.
I think there were a few more questions in the chat. So
yes, Linda has another question. Maybe Linda, if you want to.
Yeah, I'm here. Hi, everybody. Okay. Thank you very much to everyone organizing and presenting. I would like to know, because I arrived late, if you could go back to the justification of your choice of model initially. I arrived around 2 p.m. So.
Not sure. Are you referring to a particular slide or?
I'm sorry, I think I missed it. Just where you explain why you chose GMRF, or why you chose, your different.
I think the GMRF is one of the standard models that are used to capturing spatial dependencies, and this is, you could say, an attempt at generalizing the GMRF and finding connections between GMRFs and CNNs that are also standard models, but in a different application domain, computer vision, but which at the same time, they have some similarities, as we said in the beginning, that you can kind of view spatial data as images as well. So we wanted to explore this connection and see if we could link the different model classes.
Okay, and the link with the CNN?
Yeah, the link with the CNN comes from the fact that we use the CNN to construct the deep GMRF. Okay. And we then show that at least some particular choices of standard GMRF models are special cases of the deep GMRF.
Okay, thank you very much.
Okay, another questions from Duong in the chat.
So my name is Duong. I'm a postdoc of Ronald. First of all, thank you very much for your talk. So I have a question that is why it's relevant, but I think that I would like to ask this question because I got the same problem when I work with NPO. So is the model repeatable or reproducible now? And in your table, how many runs did you use to create this table? Did you get the best result for each model, or you get the average for each model? Thank you very much.
Yes, I believe that the results are reproducible and the code is available. At least I think it is. If not, I mean, it's just a matter of contacting Per, who implemented the model, to get the code. And when it comes to the results here, these are, believe it was a long time since we actually looked at this, but looking at this table, I believe that these are average over like 5 independent runs or something like that. So it's not cherry picking the best results, but still it's just the results that we got from these 5 particular runs. But it's not an exhaustive evaluation in the sense that I can't guarantee that you will always get good results. It could be that you occasionally diverge when optimizing the model or something like this, but we haven't explored it in that level of detail.
Yeah, so in the parentage, I understand that is a standard deviation of 5 runs.
Exactly.
Right?
So we report here, and it looks a bit funny. The table, it's a big table, I know, but for all different settings here, we just report the mean, and then for this one, which we said was the best performing model, we also report the standard deviation. And this is just because we don't want to further overcrowd this very populated or like messy table with more numbers.
Yeah. For example, for the inter data set, the average of C15 by 5 is 8.14, and just second best, and for L is equal to 3, the result is 8.29, but the standard deviation is 0.461. It is quite important to what I want to say is the standard deviation maybe play an important role to compare the result of the model, because the difference between the mean value is not very significant.
Yes, I agree. We could definitely report more numbers here and look at how the different models perform, and also I think test the models on other data sets would also, of course, be interesting to see if we can get consistently good results, sort of.
Yes, and another question, please. And how long do you take to train a model?
I can't give an exact number, but it's not too bad. It's sort of on the order of a few hours, maybe, for this data set. On like a standard desktop machine with a GPU. But it's still, I don't know, to be honest. I think I asked about it a while ago, but it was some time ago, so I can't remember exactly.
Yeah, okay, thank you very much.
I think it's still, it's more computationally efficient than actually solving the GMRF problem exactly if you would just try to compute these matrix inverses and so on. So we do gain by using the variational EM approximation and the CG method and so on. So in this problem we have, I think, a bit more than 100,000 pixels in the image. So it's fairly large in that sense, the number of variables that you need to work with and store in memory. And if you would need to actually construct the precision matrix explicitly, it would be a matrix of size 100,000 plus times 100,000 plus something.
Okay, thank you very much.
Yep.
Okay, thanks. I think I may have another question. It was in slide 16, I guess, if I remember well. So no, it was not in slide 16, but it's not that bad. I think it was related to the number of layers required in the deep GMRF. Yeah, it's this one, just the slides before. You precise that for Matern GP, you need a number L that is larger than the smoothing parameter.
Yeah.
I think the smoothing parameter, it relates to the SPD that you shown in slide 9, something like that.
Yes.
And this SPD, it's an isotropic one that you shown. I was wondering if these results hold when you modified a bit the SPD to, I don't know, model some more complex anisotropic fields, or if you add, for example, some diffusion parameter in your SPD, does that result hold? I'm not sure, in fact.
I'm not sure either, to be honest.
Because it's true that, for instance, if you have a very complex local diffusion parameters, it seems, and a smoothing parameter that is 2 or 3, it seems quite very low number of layers in the deep GMRF to retrieve all the patterns in the image, but I don't know. Because I guess one of the main advantages of using a lot of layers in the deep GMRF is to be able, even with this plus filters, for instance, is to be able to retrieve even anisotropic structures. But you probably need a lot of layers if the diffusion parameters are quite complex over space, for instance.
I think the way it's set up, it will always be it will always model a stationary field in the prior, because we use the same filters sort of everywhere. If that's what you're referring to.
Yes, okay.
But it will be the more, so I mean, another way of thinking about the model is that when you stack multiple layers, you could equivalently just take these individual filters for the different layers and compute a larger filter by convolving them with each other.
Yes.
And then you can think of this as being sort of a standard GMRF with this larger filter, which has a very particular structure.
Okay.
So essentially, we end up with a model which is it's a GMRF on the lattice, but with edges going multiple steps, depending on how many layers we take. If we just have one layer, then you would just connect neighboring pixels.
Yes.
If you take 2 layers, you would draw edges to the neighbors of your neighbors and so on.
Okay.
So it will result in more long-range dependencies in the model. And that's kind of what I referred to before when saying that we could essentially just model this with a very large convolutional filter, and assign free parameters to that and try to learn those. But that will be computationally very costly, because there is no equivalent of these kind of the cheap determinant computations in that case.
Okay, thanks. Ronan, I don't remember if you had a last questions earlier.
Yeah, maybe not a question, but more a comment or some kind of proposal for collaboration, maybe. We have very, as I mentioned, we have very related ongoing research, but up to now more based on deterministic formulation than truly stochastic one, as we want, but based on a variational formulation and more for application to space-time dynamics. But basically, it also applies to spatial, and especially Maxime is moving towards the extension of what we've done up to now to the stochastic component, including extension to stochastic PDEs that relates to the kind of Gaussian representation you've presented, and possible extension to non-linear representation. And that could be interesting to interact on this and possibly share data sets and experiments. In our case, we're also interested in application to satellite data, specifically for ocean remote sensing, for temperature at sea surface or current at sea surface, those kind of things, but very much related to the kind of example you've shown if you had the time dimension. And that could be interesting to know how the different, because there are many different ways to state the models, even they are very close in the specific implementation, either of the different models in terms of architectures or of the learning part and the inversion. We consider, for example, for the Q parameterization in the variational inference, or that would be interesting, I think, to maybe to share data sets and common evaluation frameworks or case studies to know what the. So I don't know if that's of interest for you.
Definitely, I would be happy to discuss further and see if we can find some grounds for collaboration. And as you mentioned, the data sets, since I'm coming more from the methodology side, it's always interesting to find real applications for this to try the methods on. So
okay, good. So maybe to be pragmatic, practical, what we could do is we may come back to you with Maxime in a short time, a couple of weeks, I would say.
Yep.
Maybe to discuss what we've been doing, something very much related to what you've done, but connected also to this variational framework I mentioned before for space-time interpolation issues. That could be starting a specific discussion and maybe then share the case studies and start some joint work on this. That could be something.
That sounds great. So I actually have a PhD student now, a fairly fresh PhD student working on an extension or working with this model and different extensions. I mentioned that we're looking into the space-time domain as well, and that's something that we have on the to-do list. Currently, he's focusing on generalizing this model to arbitrary graphs. So now in this talk, I only presented for lattice-based graphs, but we're also interested in applying the same ideas to arbitrary graphs. So there are a lot of things that can be generalized and improved, I think, here.
Okay, great. Then. Okay, so Maxime and I will come back to you.
Yes, of course. Yes.
Before the summer break, some point.
Sounds good.
About to schedule things. Okay, thanks again. That was. I don't know if Maxime mentioned this before. I recorded the session today. If that's